Hello, and welcome to the video portion for the first Assemblies lab of ME123. Assemblies are a new file type in SolidWorks, which allow you to combine multiple part files into a single model. Within an assembly, you can also create relations that allow parts to move with respect to one another. Let's begin by creating a new assembly. For the first time this quarter, we're going to go and open up a new file. But this time, instead of part, we're going to select assembly. Shocker, I know. First things first, when we open a new assembly, we get this sidebar over to the left. Part files that we already have open will show up in this little window down here. If you don't see the part that you want, you can always hit Browse and go digging for it. If you don't have any files open, the Browse window pops up automatically. The first part of your assembly holds some special meaning. The first component that you add acts as an anchor, or the thing that everything else is defined relative to. If you're building a robotic arm, you probably want to use the mounting bracket as the first component. Likewise for the frame of a car or the base of a lamp. Try to think of the part that stays in the same position or orientation while your assembly functions, and use that as your initial component. This can be fixed or changed later in the design process, but it's a real pain to pull off, so spending some extra time to think it through in the beginning is usually worth it. For today's example, we're going to be assembling a simple robotic arm, so the base makes sense as our first part. We can left-click to select it from our open documents, and then hit the green checkbox up at the top left to place it. Great! Now, before we go any further, it's important to set the units of our assembly. This works just the same as it does in part files, and you can select your units from the little drop-up menu down here. Unless you have a good reason not to, it's best to make sure that the assembly units match the part file units. The earlier you set your units in an assembly, the better, but assemblies are more forgiving towards later unit changes. Okay, now, there's two competing schools of thought with respect to putting together assemblies. You can either bring in a piece, define it, and then bring in the next piece, and repeat until the whole model is assembled. Or you can bring in all of the pieces at the beginning, and work through everything until it's all put together. Both methods work, but I'm used to the dump out all the parts on the floor technique, and it's my video, so that's the one that we'll be using. Anyway, now that we have our first part brought in, let's take a quick look at our user interface. As we can see, our assembly startup page is pretty similar to the part file. We've got a design tree over on the left, and a ribbon up at the top. We can see that our design tree has its own three primary planes. If we keep going, we can see that our initial part has a drop-down next to it. And after activating the drop-down, we can access all the features, planes, and reference geometry that were used creating that part. Because this is the first part that we brought in, and because we placed it with the check mark, we can see that its primary planes match up with the primary planes of the assembly. Alright, now let's start bringing in some of the other components. We can go up to the Assemblies tab on the ribbon and select Insert Components. Before we get into the actual process, I want to point out this pin button here. Activating it is going to keep the menu open in between placing components, which is going to save us a decent amount of time as we continue forward. In any case, the first part that I want to bring in is the rotational joint. Before placing our component, we can see that we also have a Configurations drop-down down at the bottom of the menu. If your part has multiple configurations, you can choose them from the drop-down. Let's start by bringing in the socket component, and then we can pop back over to the menu, change our configuration to plug, and place that next. Continuing along, we'll bring in one joint interface, or arm section, one of these lid pieces, and then we'll bring in one of these switches. One cool thing about assemblies is that you can actually import an assembly into a different assembly. When an assembly is used like this, it's called a subassembly. Here, I'm going to choose this linear gripper as our next component, and then we can left-click to place it in the view window. Subassemblies are handy when there's a multi-part component that's repeated, or when there's a complex component that you want to be able to interchange within your model. For example, I also have a rotational gripper subassembly that we'll be swapping with the linear gripper later. Anyway, now that we've dumped out our pieces, let's start putting the model together. You can move components by left-click dragging them in the view window, and you can rotate them by selecting the drop-down under Move Component on the Assembly tab and selecting Rotate Component. From here, you can left-click drag to move the component in a three-dimensional rotational space, which is in general frustrating, and fortunately for us is not the only way to do this. Similar to how sketches have dimensions and geometric relations to properly position geometry, assemblies have mates. A mate allows you to apply a geometric or numerical constraint between components in your assembly, reducing the number of degrees of freedom. Each component comes with 6 degrees of freedom, 3 translational, as we can move it in the X, the Y, and the Z direction, and 3 rotational, spinning them about each one of the 3 axes. Today, we're going to focus on standard mates, but the next lab will delve deeper into the advanced and mechanical mates. Okay, where to begin? Let's start with the joint, since that seems fairly straightforward. I'm going to bring up our mates toolbar by hitting the Mate button up on the Assemblies tab, and from here we see that we have a peg and a socket that need to be connected together. And both of these components are cylindrical. The concentric mate looks like that ought to do the trick. We can left-click that, and then we can choose two circular or cylindrical components, and SolidWorks moves them to share the same axis. Concentric mates generally remove 2 translational degrees of freedom and 2 rotational degrees of freedom. We can see that when we finalize the mate, we can left-click drag the components so that they can move relative to one another, but they are now linked together. However, there's still this gap that I would really like to be able to get rid of. Let's try connecting these 2 flat surfaces together. In a sketch, connecting 2 things together is a coincident relation, so let's try the coincident mate and see how that functions. We can left-click to select our 2 surfaces from the view window, and when we're done, we can see that the joint itself gets connected together. Last but not least, for this component, we need to connect the joint up to our base, so we'll select concentric to get the peg to fit in with the little hole down at the bottom of the base, and then another concentric to match the center point of this sphere with the center point of this sphere. Great! Now that it's fully mated together, we can left-click drag on this joint in our component, and we can see that it moves freely, and it spins around, actuating as we would expect, but it doesn't fly about anymore. Of course, we can also see that the joint can now be moved so that it intersects with our model, which is not necessarily what we were looking for, and it does kind of break how things are supposed to work in the real world. Generally, when 2 things collide, they stop, but SolidWorks does not default to having object collision. We can activate object collision temporarily by selecting Move Component and then checking the Collision Detection box, but this option isn't turned on its own. This means that pieces of your assembly can intersect with one another, and it's up to you to provide the proper advanced and mechanical mates to stop the collisions. Of course, depending on your application, it's often okay to allow for the model to self-intersect, but you want to make sure that parts aren't clipping into each other in the assembly set you turn in. One of the easiest ways to find intersections is up here on the Evaluate tab in the Interference Detection tool. When you run the interference detector by hitting the Calculate button, SolidWorks finds each instance of interference and colors it bright red. So we can see we have one interference here, where the peg of the joint is clipping into the walls of the hole, and one interference here, where the joint is clipping through the side of the base. This second one seems easiest to fix to me, so we'll start there. We can just exit out of the menu, and then left-click drag to move the component to a place where it's no longer intersecting. The peg one is a little harder to fix, but it is still possible. The problem here is that the peg diameter for this joint is too large for the hole. Depending on the model, you may want to decrease the peg's diameter or increase the hole's diameter. The peg seems more obvious to me, so let's change that one. While we're in an assembly, you can actually edit the parts that you've brought in. First, we find the part that we want to modify in the design tree. Then we can right-click and select Edit Component. And this brings us right into the interface that we've used on our previous part files. From here, we can go into the part, hit the drop down below Revolve to, right-click our sketch, and select Edit. I'm going to change the sketch diameter down here from 30 units to 20 units, and then we can hit the Edit Component button up at the top left to rebuild our part using the new dimension. To note, changes made to components will actually go back and modify the part file itself, using SolidWorks' built-in bidirectional associativity. Be careful when editing components, as this will change that piece everywhere else that it shows up. Also, when it comes to part files, you want to make sure that you don't move or rename any of them in your file directory. The assembly file does not actually contain the part files itself. It uses the names and locations of these part files to keep up to date. Moving or renaming them leads to reference errors, so it's often best to avoid. Okay, at this point, we've noticed that we probably don't have enough components to make the entire arm. The design that I have in mind has 3 joints and 2 arm sections, but we only have 1 joint put together. Fortunately for us, copy-paste functions within assemblies. You can hold down the Control key and select the components that you want to copy, hit Control-C on the keyboard, left-click in the view window, and Control-V to place a duplicate. The cool part about this is that it also copies the mates that were used to put these components together. We'll repeat the process one more time for a second ball joint. We'll duplicate the arm section once, and then we'll duplicate the switch 2 more times. There we go. That looks like we're good to keep assembling. Back to our mates. Coincident and concentric are 2 of the most versatile standard mates, so oftentimes you can get away with just selecting the surfaces that you want to mate together, and SolidWorks will pick the mate that works best, though it's always important that you double check to make sure that it's selected the right one. Additionally, sometimes the mates that you add can have their alignments swapped. For example, if we select this surface here, and then this surface here, we see that we have 2 options down at the bottom for mate alignment. We can select anti-aligned, which is what it defaulted to, or aligned, which swaps it to the opposite direction. If your mates ever look like they've been reversed from what you were expecting, try selecting the other option and see if that fixes it. There we go. I've taken the liberty of applying all of our coincident and concentric mates to put all of this together. Let's take a look at some of the additional standard mates. These ones tend to be a bit more situational, but they're still very useful in their given situations. One that can be particularly handy is the parallel mate. which sets two planes to be parallel, as one would expect. Here I've selected one surface on our gripper and this top surface on our base to ensure that the gripper remains planar. Similarly, we can apply a perpendicular mate by selecting the surface of our base here and the bottom face of the lid in order to make sure that the switches are always accessible. The distance and angle mates function just the same that distance dimensions and angle dimensions do. Let's take this first switch and set it so that it has an angle from this surface to this surface of 45 degrees. If it didn't quite measure the angle the way that you expected it to, we can swap it around by hitting the flip direction checkbox, changing the mate alignment option, or both. We can then set up a distance mate to ensure that the origin of our assembly and the origin of this bit of the rotational joint are always 350 units apart. In addition to the origin, you can also use the primary planes and reference geometry of the parts as inputs for your mates. This can often be a useful trick to help center things or to get behavior that may be tricky to pull off with just the geometry of the models. Last but not least for our legal standard mates is the tangent mate, and for that I want to put something in the gripper, like this bubble wand. Just like in sketches, the tangent mate allows us to enforce a just touching condition between two surfaces or edges. With the tangent mate, the mate alignment often comes into effect, where we can see that depending on the mate alignment, our part can be on one side or the other of the selected face. We can go about mating in our bubble wand, so we'll connect these surfaces together so that it sits in the palm of the hand. And then we can go about adding in our other two tangent mates, one to connect in this top finger, double checking the alignment to make sure that it's set properly, and one more to connect in the bottom finger. So we'll select that surface and this surface. Apply our tangent, hit our checkbox. Well, that's not exactly working out the way that I want. It's almost as though the fingers of the gripper aren't actually capable of moving. This is because the gripper subassembly is currently set to rigid, meaning that the entire subassembly is treated as an individual component. In order to fix this, we can right-click on the subassembly and select Make Subassembly Flexible from the context menu. This allows all of the components in the subassembly to now move relative to one another, allowing for our final tangent mate to be applied. Connecting in our cylinder to this final finger surface, hit our checkbox, and we're good to go. Now, there's one more mate on the standard mate section, and that's the lock mate. Similar to the fix relation, the lock mate is off limits for this course. It freezes the selected component into an arbitrary location in space, and it doesn't provide any information as to exactly where that is, which makes it difficult to work with. One thing the more astute of you might have noticed is that even with all of our components mated in place, the assembly is still considered underdefined. This is because SolidWorks still sees unconstrained degrees of freedom within the model, meaning that certain pieces of the assembly don't have anything limiting how far they can move. In contrast to parts and sketches, it is okay to leave an assembly underdefined. A car's wheels are allowed to spin, this robot's joints are allowed to rotate. The important thing is that the assembly is defined enough to show your intent. You can see which parts are underdefined based on the little minus signs next to them in the design tree. Up at the first component in our design tree, we see that it has a little F next to it. This tells us that that component is fixed in place, which is what's keeping that component from moving within the assembly. You are allowed up to one fix per assembly, and it's usually going to be the first component that you bring in. But you can technically change this. First, you right-click on the component and select Float from the context menu. However, this does de-anchor the entire assembly in space, meaning that now the whole thing can move freely. In order to fix this, we're going to need to anchor a different component. One of the easiest ways to do this is through mating the primary planes of the component, in this case the front, top, and right of our base, to the primary planes of the assembly, which can be seen at the top of the mini design tree. Though possible, this can be a kind of cumbersome task, so oftentimes it's best to spend a little bit of extra time at the beginning to really think about which component you want to be the initial component of your part, instead of going through the process of changing it later. Okay, now that we have all of that set up, we have a few more things to cover. First, what do you do if you don't need a part or a mate anymore? In order to delete or suppress a mate, you can first find the mate in the little subfolder below the component, or through the mates folder at the bottom of the design tree. From here, you can right-click on a mate and then hit suppress to temporarily remove it, or you can choose delete to get rid of it forever. The same process functions for parts as well. Next up, configurations. Just like part files, assembly files can have their own configurations. The process is pretty much identical too. You can go to the Configurations Manager up above the design tree, right-click, and this time we'll make a new configuration called Rotational. And then we can apply our changes as desired. In this case, let's go back over and we can suppress the linear gripper and our bubble wand via right-click Configure Component. and then we can check our boxes for the configurations that we don't want them to show up in. While we're here, you can also see that there's an option to change the configuration of that component within this configuration of the assembly. To wrap up our changes for this new configuration, we can import our rotational gripper, place it into the model, and then apply the relevant mates. Once that's mated in, we can then right-click on that sub-assembly, go to Configure Components, and ensure that it's suppressed in the default configuration. As always, once we're done modifying our configurations, we want to double-check to make sure that both configurations still function. Following the same process, you can also turn mates on and off across configurations. Last, but definitely not least, we can apply some appearance modifications. SolidWorks Gray is not the most appealing color to look at, and having a lot of components of the same coloration can make it difficult to tell pieces apart in a complex assembly, so adding some color can really help make things easier to see. We have a visualization video that goes into the details, but let's look at the simple options while we're here. We already know one way to change colors, and that's through changing materials, but that does leave a lot of options out. We can get a lot more control over our appearances by selecting this button here, choosing the component that we want to color, and then choosing the color that we want to change it to. With coloration, there are two levels at which it can be applied. At the component level, which is only going to change the color for that specific copy of the part, or at the part level, which allows for a lot more granularity in exactly what you're coloring, as you can choose between surfaces, features, or bodies. But it does modify the part file itself. You can think of the component level as buying a car and spray painting it in your garage, and at the part level as changing the color specs at the factory. While we're here, instead of modifying the entire part, let's just change it so that an individual surface of this arm piece is blue, and we can see that the other arm piece also has the corresponding surface changed color. No matter what changes we make while at the part document level, they will be applied to every instance of that component across any assembly that it shows up in. Anyway, that's all that we have time for in this lab. We'll be getting further into assemblies in the next video. Assemblies are very powerful, and SolidWorks is capable of making some very impressive and complex models through this toolset. As always, experiment and mess around to see what you can do with them. Thank you, and we'll see you again next time.